Alright, welcome to the midterm review, and the first thing that I'm going to say is when I write code, I'm going to write my code in the Lecture 12 folder, okay? This is like technically Lecture 12. Okay, so just so that is clear, I'll put it right there. Maybe we can make it italic, who knows. So your test has some stuff from the book. I took some multiple choice questions out of the book, and pretty much the only stuff that I can ask you about are things about complexity and lists and like algorithms that it's talked about, like linear search and binary search. Those are pretty recent. So let's talk about complexity and lists first, because that's going to be the first part of your test. So complexity, the things that I'll test you on is pretty much big O notation. And like converting an algorithm, like counting the steps. You don't have to count them exactly, but I want you to be able to create the big O notation version of any algorithm. Okay, so just get that under your belt, and I won't ask you like big omega, big theta, things like that. So just remember the rules. So you count the steps. Step 1, count steps. And you don't have to do this very accurately as long as you remember the little tricks. So it doesn't have to be too accurate, as long as it's accurate enough. In terms of input size, usually we say n. There are cases where we use something other than n, but usually it's n. And so step 2, after you get some size, you somehow counted 2 plus 42n plus 43n cubed plus 44n to the 14th. That's your algorithm. Then you need to remember what to do. So step 2, oh no, we're still superscript. Step 2, drop lower order terms, because those are going to go away with the mathematical definition of big O, remember. So all these guys are just going to get blown out of the water by this biggest term here. And you're going to have to go and find that. All right, so drop the lower order term. So now we have, now we have just 44n to the 14th. It's our job to do something with that. Okay, we found the biggest term. What are we going to do? Well, the final step is drop any constant multipliers. Because the 44 doesn't really matter when you're given n to the 14th, putting that up against n to the 15th, for example. That'll just go away for larger functions. So it's all this stuff is coming out in the wash, I guess. I want you to think about, like, sure, this is n squared, or this is n squared, and this is like 4n squared, but really, when you're comparing it against something like, I don't know, some exponential function, which I will put in green to differentiate, we don't really care about the constants anymore, okay? It's just going to grow so much faster anyway, it doesn't really matter. Okay, it's all about assume that n was 1,000,000, 2,000,000, 1,000,000,000. Those are the numbers that we care about at the moment. We want to know, as these numbers get large, which term wins out? What does it really all mean? Okay, so this finally becomes n to the 14th, and then you can just put an O in front of that. Okay, so big O, n to the 14th. Oops. And that's the answer. So that's complexity in a nutshell. You're going to figure out the steps that are involved, and remember straight lines of code, just a few of those that don't call any functions or do anything fancy. That's always O of 1 if they don't do anything fancy. The second you start looping, you have to figure out how many times it loops. How many times do we loop? And also, you need to worry about, well, how many iterations, or in each iteration, how much work does the body do? So for example, if I made a loop that, I don't know, for I equals 0, I'm going to use pseudocode. For I equals 0 to I equals, I don't know, 42, do something. Or sorry, let me use n. For I equals 0 to I equals n minus 1. There's a big difference between, like, C out I, or I guess if we're using pseudocode, we might as well go all the way. Print I. There's a complete difference between this code and dun dun dun. Code where the body of this loop does something fancy, something that's not constant. Because right here, this is the body of the loop, it's constant. So together, it's like n times a constant, which becomes O of n. But if I do something fancy inside a loop, like, I don't know, draw a n by n box each time, so maybe it's like making a 3D box now, somehow, this is accomplished by another loop, most likely. So either you're calling a function or you're writing another loop inside of the loop, and this is going to take, well, it depends on how you want to think about it. It's most likely going to take n squared time to draw that box. So that's O of n squared. And we're doing that n times. So times n, which comes out to be O of n cubed. You're doing an n squared thing n times. I hope you see how that's working. So that's the idea there. And always for complexity, you want to use the tightest bound. Otherwise, I will mark it incorrect. Okay? That's a huge key, because yeah, sure, this and this are both O of 2 to the n, but that's telling us nothing about the running time of the algorithm. Okay, we want the tightest bound, the smallest possible thing you can put inside of the O. Okay? That is, I guess, complexity in a nutshell. Feel free to come to office hours and yell at me about anything else before the midterm. That's essentially what I want to say there. So I guess as soon as you get comfortable counting the steps, the rest of this is not too bad. Okay? Alright, welcome to my second edit. Let's move on to lists, and they are like arrays, but not. Alright, so you can hold a bunch of stuff inside of your lists, but they're kind of separated in a sense. When you had an array, it was like 1, 2, 3, hey, they're all there, having fun. Whereas there's some social distancing going on when you have lists. You got your one node, it exists by itself, and you got your 2 node, 6 feet apart, and you got your 3 node. Okay, so that's the real separation. Maybe you have a first pointer and a last pointer. And you can add nodes as needed. So say you wanted to put a 0 node in the front. This is much easier to do than arrays, whereas you need room in an array, first of all. And then you'd have to, if you want to put a 0 there, you'd have to start shifting everything over. And that's no fun. For a linked list, it's super nice, because you can just make that new node. Be like, hey, here it is. There's your next node. It was whatever the first used to be, and first is now this. Isn't that beautiful? So to add a node to either the front or the end, you just need to mess with a couple pointers. All right, and that's going to be O of 1. Constant time. To remove a node from the end, it depends on whether you're a doubly linked list or not. So what that means is it's super easy to, it's also constant time to remove from the front, okay? Because you can just change the first pointer to be like, it's just whatever the next one was. To change the last pointer, though, that's difficult. So if you're on a singly linked list, and we want to set the last pointer to be not there but here, it's hard to find this node, okay? There are doubly linked lists, which you've been reading about, I think, that have a previous pointer, which would be useful in this case. But for our case, when we're using a singly linked list with just next pointers, we have to iterate from the first node all the way to the second to last node. And that's no fun. Okay? So it really depends. To remove from the end, it could be linear. to have to go and find that second to last node. That's n-1 things you need to do, n-1 iterations of a loop. So just think about that. I'm only going to ask you about singly linked list stuff, I think, at least in my questions. The multiple choice questions might have something about doubly linked lists, but it will just be stuff from your book that you can go and search for, because you're going to have your book next to you. And yeah, I just want to make it clear that insertion / removal / search, sometimes you need to get somewhere. And I think this is a horrible way that I wrote this. Let's do it again. So to get to a node in the middle, you have to iterate. Oops. You're most likely going to have to iterate. Unless somebody, like, the clouds parted and somebody gave you a beautiful heavenly pointer to the middle of a list. That's most likely not going to happen. You're going to have to find that thing. All right? So, for example, searching for something that's in the middle of the list, well, you gotta iterate from the first. You can't go backward from the last, unless you're a doubly linked list, of course. Somehow, if you need to get there, you gotta iterate from the start. So sometimes it's O of n to do a lot of stuff, other times it's O of 1. So just think about those things. Can I immediately add a new node? Yes, because I can set the last pointer as next pointer. And same with first, but kind of in the opposite way. Okay. Can I delete things super easily? No. Can I search for things super easily? From the front, super easy to remove. Boop. I can follow this next pointer. From the end, it's super hard to remove. I need to somehow get this thing. And then that will be last. So just keep that in mind. If you ever think you need to iterate, and I encourage you to work through these examples in your mind, if you ever think you need to iterate through the list for some reason, then it's suddenly going to become a linear time algorithm. Okay? So it's always easy to insert / remove at the front for any kind of list, but the end may be hard. Okay? But removal may be hard. Let me say that, because it's still easy to go to the end and add something. Okay, it depends on whether it's a singly linked list or a doubly linked list, which is fun words, and you won't really have to worry about it for your lab at least. So with that, I want to go on to just a really large example with just a counter class. We'll be able to say something like counter C, and this makes a counter called C, and it'll hold a count. But I want to make that count a place on the heap, okay, so that we can talk about the big three, of course. So let's talk about the constructor, the get count, and the custom ++ operator. Just a potpourri of things that we've learned about. So here is my counter folder, and I've made this inside of my code from class folder. I pre-made this for you. Okay, so inside of counter.h is going to be the stuff that we care about for now. So I have a constructor, I have a get count variable, and of course it's const because we're just going to get the count, and then I have a ++ operator. And so in main, we can use it like this. We can say counter C, ++ C, all day long, get the count. Okay, so this first part, if we just disregard the rest of the output, it's going to print out 4. Okay? /main. And don't worry, we're going to get to the makefile as well. So it'll print out 4. And the implementations of those are pretty straightforward. So here's the constructor. We just got to make a new int. The ++ operator, we just got to add 1 to the int. And the get count, we just got to return the count after dereferencing it, of course. Nothing bad. And of course, we can split this up into multiple files like I did. We can make a counter.h, of course, with these header file guards so that we don't infinitely include things. We can put the implementation over here after including counter.h. And then in main.cpp, we can start using our library. Okay? Hopefully that's not too bad, and splitting it up in that way is super nice. So, and then you can make a main file, or sorry, not a main file, a make file to go and compile all this stuff. So, for example, I want to make main at the end of the day, and I want to be able to just recompile the parts that have changed. So I'm going to go separately through separate compilation. I'm going to compile main.cpp into main.o, compile counter.cpp into counter.o using the -c command. And these are my rules. Remember that for make files, it always goes target : requirements, and then a bunch of possibly multiple command line commands to go and make that target. So for us, it's a bunch of G++ calls. And so once you have those things, it'll go and make them, and then we can finally link them together. This is a linking process into something called main that we can go and run. And if we had like a clean, that would go and remove everything. I can show you this all from the beginning. So remove counter.o, or remove everything.o, please, then also main. Okay. Make clean will remove all that stuff. Now there's nothing there. Now if I say make main, it will recompile counter.cpp. It needed that to make counter.o, main.cpp to make counter, or main.o, compile, or sorry, link counter.o and main.o together into main that I can then run. And the beauty of make files is separate compilation. I can change one thing and not have to worry about the other. So if I say main.cpp, I don't know, get rid of one of these things, suddenly it becomes 3. Okay? So, and I only had to recompile, you see, main. Whereas the original time I had to compile counter. Counter didn't change, I changed main.cpp only, so I only had to recompile that and then link it all together. Linking is quick. Alright, so that's a brief segue into make files and main and things. Let's see, let's make sure this is all recording, yes. Okay, the big 3. Boop. Let's do the big 3 now. So we got your Destructor, your copy Constructor, your copy assignment operator. Beautiful stuff. It's all working. And the idea is, the point of it all is to make a counter C2 from C and not have it be stupid. So we have C2, it has a count inside of it. The default copy constructor, for example, just points to the same place in the heap. And so changing C2 changes C's count. No, no, we do not want that. No, no thank you. So with that, let's do it the right way. We need to make a deep copy, remember? All of those deep copies. So we're all about decopies. And we want to delete memory when counters get reclaimed as well. If we use the default implementation and we added a destructor, suddenly we try to delete the same place in the heap twice. Gosh, that's horrible. So we want to be safe. All right. So what we'll do for the destructor is to just delete the thing on the heap, that one thing that we made for ourselves. Okay. And then for copy constructor, what we want to do is make a deep copy. So we're going to make a new place on the heap for our count and just set the other person's count into ours. Okay? And then the same for copy assignment. You first need to check for self-assignment. Watch out for that. And then do exactly the same thing, in essence. Make a deep copy of the other person, and you're always going to return yourself so that you can chain those commands, if you remember that. You can be like C3 equals C2 equals C1. That's the reason for it. That's all. Not a huge deal. Just remember the process. And let's see here. Space and time complexity. Well, these are all straight lines of code. This is one assignment statement, just returning a thing, returning nothing but incrementing count, so you're doing a plus operation, some dereferences. This is all nothing involving loops, just straight line code. You're only holding one thing inside your counter. So all of these, including the fancy ones, are constant time. Yeah. Space is also constant. Sometimes you're not storing anything extra. Like some of these functions, they don't have any local variables. Parameters count as local variables. So this one and this one, they do have technically a local variable. It's a reference though. It's not getting copied in the way you think. But you're always using some space when you're calling a function. Like say main calls that plus plus operator. You still need to make room on the stack to know where to return to. That's part of the stack. That's what it gives you. So you're still storing some information as long as every time you make a function call. Okay, that's the thing. Whee. And then when you push, or sorry, when you pop, it goes all away. Okay, That's what I want to say about that. The last thing is test cases. How do you know if it's all working? Well, I've just made some very simple ones. Here's my test cases. What should happen is, I'll just do a test case in a comment. C2 should be a copy of C. So at this point, yeah, C2 should hold a count of 3 also. And now C2 should hold 4, a count of 4. And C should still be 3. So you can make your test case. You can be like if, or assert true, C.getCount is equal to 3, and C2.getCount is equal to 4, things like that. That's the idea. Now we can quickly make a assert true function. Void assert true, bool b string description. If not b, cout failed description. Otherwise, cout passed description. Okay. And then the rest of these, it should be pretty straightforward. Was it not happy still for some reason? Did I call it something different? No, assert true, sorry. Oops. How about that? And you could make as many of these as you needed to. Like for this one, to check the copy assignment operator, again, you'll check all the counts again, perhaps. And we passed our test. Okay. So yeah, that's essentially testing. Just figure out what it should be and check that, right? Check what you expected with what you got. All right. And then finally, just vectors, super quick. There's not a lot going on that you don't know about. You've implemented them now. So vectors are just, well, they're a dynamic array, so that array can grow in size, potentially, it can double. And you need to keep track of your current size so that it can double. So you got, inside of your vector v, you got your size, maybe it's 3, you got your capacity, maybe it's 4, and then you have your array itself that lives on the heap, just like that. And pushback is really hard to analyze. It's really constant, and I encourage you to look up why, but it's nothing I'm going to test you on. But understand, like, simple functions like size and at. Those are constant. They're not doing too much. Okay. Pushback is fancy, and the way you implement it, remember, is if there isn't space available. So we're trying to add something, but our size is our capacity. We need to somehow double. We need to start doubling our array to twice the size, and we need to copy everything over. Okay, so maybe study the slides for that one, but it shouldn't be too bad. And I think that's about it. That's all I wanted to talk about. So yell at me if you have any questions. Good luck on the midterm. It shouldn't be too bad because you got your book in front of you and all of the code I've written, all these slides. Yeah, so with that, study hard, and I'll see you later.